This is section 8.4, in which we will use trigonometric substitution to simplify integration. Okay, you're all familiar with sine squared plus cosine squared equals 1, but there are other trigonometric identities that we can use to simplify integration. Throughout this section, I always find it helpful to draw a picture of a triangle and put the quantities around the sides to help me understand the relationships. This is not required, but again, I think it's very helpful. Here are 3 trigonometric identities that we can use. The first one, cosine squared theta is equal to 1 minus sine squared theta. Then we've got secant squared theta is equal to 1 plus tangent squared theta. And tangent squared theta is equal to secant squared theta minus 1. Okay, to use these are the triangles that show the representations. This one is useful for square root of a squared minus u squared. We're going to let u equal a sine theta. And on my triangle, this is a, this is u, and this is the square root of a squared minus u squared. If I had an integral with a squared plus u squared in the radical, I could let this hypotenuse equal that amount. And then this side would be u, this side would be a. And then a squared plus u squared would equal a secant theta. And the last one, if I have a radical u squared minus a squared, I'll put that over here. Which will put a here and u here. And u would equal a secant theta. Okay, now that we've defined our different quantities, let's work a problem. So I want the integral dx over x squared times the square root of 9 minus x squared. I can see that this integral doesn't meet any of my basic forms, so I'm going to do some substitution. I can see that the square root of 9 minus x squared fits the general form of the square root of a squared minus u squared. So a is going to be equal to 3 and x is going to be equal to u. Okay, drawing my triangle. This side is 9 minus x squared. This side is x. And the hypotenuse is 3. From the triangle, I can see that x is equal to a sine theta. Here's my theta, which in this case is going to be 3 sine theta. Dx will then be 3 cosine theta d theta 9 minus x squared will be 3 cosine theta, and x squared will equal 9 sine squared theta. So substituting in here, 3 cosine theta d theta, that's from right here. And then the x squared is going to be the 9 sine squared theta. And then this radical is going to be 3 cosine theta. Okay, now I can see I've got 3 cosine theta up here and the same here, so I'm going to cancel those out. So now I have the integral d theta over 9 sine squared theta. Okay, I'm going to take the 9 out. Instead of having 1 over sine, I'm going to change that to cosecant squared theta d theta. And then the integral of cosecant squared is negative cotangent. I take negative 1/9 cotangent theta plus a constant. Okay, and we know cotangent is cosine over sine. So when I change back to my original, I'm going to have the square root of 9 minus x squared over x plus a constant. Okay, and then I can just move this 9 in here with the x, and then I no longer need the 1 there. So that's integration with a trig substitution. Here's another example of using trigonometric substitution to help us integrate. I have the integral dx over square root of 4x squared plus 1. And as before, I'm going to draw a triangle. There's theta. This side is 2x. This is that radical. And this side is just 1. And I can see that tangent theta is 2x, and secant theta would be my radical okay, and using my trig substitution, u equals 2x, a equals 1, and 2x is also equal to tan theta, as we saw here in our triangle. So now we know that dx is equal to 1/2 secant squared theta. Now I'm going to do my trigonometric substitution. Now I'm going to do my trigonometric substitution. 1/2 secant squared theta d theta over secant theta. Well, this secant is going to cancel out with one of these. So all I'm going to have left is just 1/2 the integral of secant theta d theta, which is 1/2 times the natural log of the absolute value secant theta plus tangent theta plus a constant. Okay, substituting back to my original, secant theta was 4x squared plus 1, so I'm going to have 1/2 natural log absolute value square root of 4 x squared plus 1. And then my expression for tangent theta was 2x, so plus 2x. Close out my absolute value and add the constant. In our next example, we're going to see how we can use trigonometric substitution to help us when we have a rational exponent. So here's my integral dx over x squared plus 1 to the 3/2 power. Here's my triangle. And in this triangle, this is x, this is 1, and this is the square root of x squared plus 1. Okay, the first thing I'm going to do here is rewrite this with a radical, so I've got the integral of dx over the square root of x squared plus 1, and that quantity to the 3rd power. We're going to let a equal 1, as it is here. U is going to equal x, which is also the tangent of theta. So then dx would be secant squared theta d theta. And this radical is going to also equal secant of theta. Okay, now we're going to apply substitution. So this is going to become the integral on the top, secant squared theta d theta, and underneath that, this radical was secant, so to the third power it's going to be secant cubed theta. Well, these two secants are going to cancel out with two of these. So I'm left with d theta over secant theta. I'm going to change that secant, bring it up to the top and make it a cosine. Okay, and then the integral of cosine is sine, so I'm going to have sine theta plus a constant. Okay, then when I back substitute, I get x over square root of x squared plus 1 plus c. When we're computing definite integrals, sometimes it's just easier to convert our limits of integration to theta instead of x, and we don't have to substitute back at the end of the problem. So we're going to look at an example of how that works. So I've got an integral from the square root of 3 to 2 x squared minus 3 over x dx. Okay, the x squared minus 3 has a form u squared minus a squared, even though a is not a nice integer number. So we're going to say that u equals x, a equals the square root of 3, and x equals square root of 3 secant theta. Here's our triangle. Square root of 3 is here. X is up here. And then this is our radical. Square root of x squared minus 3. Now dx is going to be square root of 3 secant theta tan theta d theta, and this radical is going to be square root of 3 tan theta. Okay, to find our limits, we're going to use this substitution. X is equal to square root of 3 secant theta. Okay, and when x equals the square root of 3, then secant theta equals 1. and theta itself is 0. When x equals 2, secant theta is 2 over the square root of 3. And theta is pi over 6. So now I'm going to rewrite my integration with these new limits. I'm going to rewrite my integral with my new limits. So I go from 0 to pi over 6. Square root of 3 tangent theta times square root of 3 secant theta tangent theta over square root of 3 secant theta d theta. Okay, don't need these anymore. Okay, what can I get rid of? Square root of 3, square root of 3, secant theta. So all that's left now is square root of 3. I have a tangent here and another one here. So tangent squared theta d theta. Okay, I'm going to take the square root of 3 out and then replace tangent squared theta with secant squared theta minus 1. Don't forget your limits here. Okay, and the integral of secant squared theta minus 1 is going to be tangent theta minus theta from 0 to pi over 6. So now I have square root of 3 times 1 over square root of 3 minus pi over 6. So this is just going to give us 1. And then I'll have square root of 3 pi over 6. And if I want to put that in the calculator to get a decimal, it's 0.0931. At the bottom of page 545, Theorem 8.2 gives you some other special integration formulas that might be helpful to you. In this last example, we're going to go back to something we did in Chapter 7 and find an arc length and use some trig substitution to help us out. So I have a function f of x equals 1/2 x squared, and I want to find the length of the arc between 0, x equals 0, and x equals 1. So we're going to use my arc length formula. We're going from 0 to 1. The square root of 1 plus f prime of x squared dx. Okay, and if f of x is 1/2 x squared, f prime of x is going to be just x. So now my integral goes from 0 to 1, square root of 1 plus x squared dx. I'm going to let a equal 1 and x equal tangent theta. And so now I have the integral from 0 to pi over 4 secant cubed theta d theta. And then this is 1/2 secant theta tangent theta plus natural log of the absolute value secant theta plus tangent theta, close my absolute value, and we're going to evaluate from 0 to pi over 4, which yields 1/2 times the square root of 2 plus the natural log square root of 2 plus 1, which is approximately equal to 1.148. For our last example in this section, we're going to revisit a problem that we worked earlier about the fluid force on the end of a cylindrical tank. And we're going to expand that a little bit by having this cylindrical tank floating in a different fluid and looking at the forces on the inside and the outside of the end of this tank. So I've got a picture here. The fluid on the inside rises to 0.8 feet above the center of the tank, which has a diameter of 2. And the fluid on the outside rises only 0.4 feet above the center of the tank. So let's take a look at these. First, I want to remember that the equation of my tank is x squared plus y squared equals 1. And then our equation for fluid force is F is equal to W times the integral from C to D H of Y L of Y dy. Okay. So we'll start first with the inside of the tank, the pink area here. And we're going to integrate from -1 to positive 0.8. Okay? And they tell us that the fluid in here is oil. And so its value for W is 48 pounds per cubic foot. So we'll replace the W with 48. And then our H of Y is going to be 0.8 minus Y. And our length is going to be 2 times the radius. So when we solve this equation for x, we get square root of 1 minus y squared dy to finish out our integral. And when we work this out, we get 76.8 times the integral from -1 to positive 0.8 of the square root of 1 minus y squared dy. dy minus 96 times the same integral, -1 to 0.8 of y times the square root of 1 minus y squared dy. So this was inside the barrel. Now we'll look at outside the barrel. And the barrel is floating in seawater. So the W value is 64. This time we're going to integrate from -1 to 0.4. .4 minus y, that's our value for h of y. And again, 2 times the square root of 1 minus y squared dy. So if I split this up, I end up with 51.2 times the integral (1 minus y squared square root dy minus 128 integral from -1 to 0.4 of y times 1 minus y squared square root dy. Okay, when we complete our details of integration, we find that the force inside is 121.3 pounds, and the force on the outside is approximately 93 pounds. Okay, this is the last example for this section. If you get stuck on the integration here, don't hesitate to contact me and I'll help you work through it.